Hi everyone, my name is Lucy and I'm studying medicine at UCC. Today we're going to do 2024 higher level question 14. So this is a long question in section B, so it's worth 56 marks in total. However, as you can see here, they ask you to answer any two of the following parts, A, B, C or D. So you only have to answer the two, you don't have to do all four, and each part is worth 28 marks each. So then 2 sets of 28, that of course adds up to the 56 marks. So today I'm going to go through all four parts of the question. However, technically you only have to answer the two. Personally, myself, anytime I did these questions, if I had spare time at the end of the exam, I would always go back and try to answer the other two parts as best as I could, just to give yourself the best chance of getting the maximum amount of marks. Because sometimes it can be difficult when you're just looking at the question to know which one you know the answers to and which one you'd be best at. So if you have time, I definitely recommend going back and trying out the other questions. So starting with part A here, this is a mechanics question and it's based on energy and there are some calculations in it as well. So let's get started. So part 1 of the question asks us to state the law of conservation of energy. So energy can be neither created nor destroyed, it is just transferred from one form to another. So this was worth 4 marks, so you get 4 marks for just this definition here, and specifically for saying that energy can be neither created nor destroyed. So next in the question, it tells us that a man is competing in a race where participants are required to slide from a raised horizontal platform down a 2.4 metre long slide. The slide is at an angle of 32 degrees to the horizontal from the platform. The end of the slide is a vertical distance of 90 centimetres above the water. So in part 2, they ask us to calculate the height of the platform above the surface of the water. So I've just redrawn out the diagram here they showed us in the question. So you can see the platform here at the top and then the slide coming down, which is 2.4 metres long. So I'll just write that in here. So that is 2.4 metres long. So that is the important information here. And the slide is at an angle of 32 degrees to the horizontal from the platform. And the end of the slide is a vertical distance of 90 centimetres above the water. They want us to calculate the height of the platform above the surface of the water. What we are looking for is the total height from all the way up here down to the water here. That is the height total. So I'm just going to redraw this a bit so that we can work with the angles a bit better and we can form a right angled triangle. So I've just redrawn out this right angled triangle with the angle in the left hand corner is the 32 degrees and the right hand side is the right angle. So this side here, the hypotenuse, that is going to be 2.4 metres. That is the length of the long slide. And so what we are looking for here, we are looking for x here, and x is the height of the slide. So that is the distance from the bottom of the slide vertically upwards to the horizontal, where the platform ends, so where the dotted line is. So looking at the triangle here, we are going to use the 32 degrees as our angle. So we have the hypotenuse and we have the opposite, so we're going to use sine. So sine 32 degrees is equal to the opposite divided by the hypotenuse. So that is x divided by 2.4. Now I'm going to bring over the 2.4 onto the left hand side. And now I'm just going to pop that into our calculator to get an answer for x. So it's important to make sure when we are doing anything to do with angles in your calculator to make sure that it is in degrees mode. So we get an answer of 1.271806234 metres. So now we have x, which is the vertical height of the slide. However, we need to find the h total. So the h total is equal to the x, which is of course the height of the slide, the vertical height. We're going to add it to the vertical distance of 90 centimetres or 0.9 metres between the top of the water and the end of the slide. So you can see here we get our final answer of 2.17 metres. So in terms of marks, this was 6 marks in total. So you get 3 marks for figuring out x, which is the vertical height of the slide, and you get 3 marks for figuring out the total height. In part 3, they tells us that the man starts from rest, calculate his velocity as he enters the water. Assume that there is no friction on the slide. So starting off with, what do we know immediately? Well, we know that he starts from rest, so his initial velocity is 0 meters per second. And we are looking for his final velocity as he enters the water. And we know that his acceleration due to gravity is going to be 9.8 meters per second squared. And we know the vertical height that he needs to go through is 2.17 meters, what we just worked out in the last question. So one thing that we also know is that if the man began from rest, that means when he began to slide down at the very start, his kinetic energy was 0, but he had a potential energy. And then when he enters the water, he has no potential energy and he has kinetic energy, which is going to equal that potential energy he had at the very top of the slide. So because of that, we are going to be using the potential energy formula and the kinetic energy formula. And we're going to say that they are equal to each other. So the potential energy formula is mass multiplied by gravity multiplied by the height, and the kinetic energy formula is a half multiplied by the mass multiplied by the velocity squared. So we can cancel out the two masses because there's one on both sides of the equation. So now we are left with GH is equal to a half V squared. So now we just want to isolate V squared on its own, so that will become 2GH is equal to V squared. So now I'm going to fill in my values of G and H, and we will get our answer for V. So then we just need to find the square root of 42.532, and that gives us an answer of 6.522 meters per second. So this was worth 6 marks in total again. So 3 marks for putting the potential energy and kinetic energy formula equal to each other, and then 3 marks for the correct answer at the very end. So part 4, it has 2 parts to it. So it asks us to draw a force diagram for the man, A as he slides down the slide, and B when he is floating in the water. So we're looking at part A here, where he is floating in the water. In this question, I've shown the man as a ball of mass. So I wasn't going to draw out a stick figure, but if that's what you want to do, go ahead. But it's easier just to draw him as a ball of mass. So you can see the man, he is coming down the purple slide here, which I showed in purple to show the difference between the forces. So you can see he has a weight coming directly downwards. And of course we know that weight is equal to mass by gravity. And however, because he is sliding down the slide, which is at an angle, so one could say it is a ramp or a wedge, because of that he has a normal reaction that is perpendicular to the surface of the slide. So that is what we are saying here. So this was worth 6 marks in total for part A. So you get 3 marks for having the normal reaction perpendicular to the surface, and 3 marks for the weight downwards. So just to note as well, with these force diagram questions, if you add in any additional or incorrect forces, you will lose 3 marks. So this is part B of when he is floating in the water. So once again, that ball of mass in the middle here, that is the man. And he is floating here on the water surface. So he has his force directly downwards, which is his weight, the same as earlier. And then he also has an upward force of equal size. Basically, it's kind of based on Archimedes' principle. So Archimedes' principle states that a body immersed in a fluid would experience an upthrust equal to the weight of the fluid it has displaced. So obviously, as the man is floating in the water, the fluid that is displaced is his weight, so there is a force upwards. That's kind of where the idea comes from. But obviously, the upward force helps him to float, because if that wasn't there, he would just sink downwards with his force of gravity. So once again with the marks, it was 6 marks in total. So 3 marks for the upward force of equal size, and 3 marks for the weight downwards. So we're on to part B now. This is based on modern physics. And so it tells us at the start that radium-224 is an unstable nucleus of radium. So immediately when they're saying that it's unstable, I'm going to be thinking this is probably about radioactivity. And it is. So we'll get into this question now. So in part 1, it tells us that radium-224 decays by releasing an alpha particle write a nuclear equation for this decay. So immediately as I start this question, I am getting my tables book open on page 79, which has the periodic table of elements because you will need it in this question. So how to answer a question like this? Well, you start off by writing out the radium. So we know it's radium 224, so the mass number is 224, radium is Ra, and then the atomic number, which you can find in the tables book, is 88. So we're going to draw an arrow here, so that is showing what is undergoing the decay. So we know that it releases an alpha particle, so that is the one. So just a side note, you can write an alpha particle either as helium or like this with the alpha symbol rather. But you just have to make sure that the mass number is 4 on both of them and the atomic number is 2. So whichever you want to write, that's okay. So I'm going to write helium here. So we know that it's released one alpha particle, so then radium needs to have decayed into some other element. So how we figure this out is you do 224 is equal to 4 plus what? So we're going to say x. So 224 minus 4 is equal to x. 220 is equal to x. So the mass number of this element is going to be 220. And then we do the same for the atomic number. So 88 is equal to 2 plus x, 88 minus 2 is equal to x, and then 86 is equal to x. So we know the atomic number is going to be 86. So if we look now to our tables book, to the periodic table of elements, you look to see what number has an atomic number of 86, and that would be radon. And radon's mass number actually officially is 222, so this is going to be an isotope of radon. The radon is shown by Or N. This is your answer here. You get 7 marks for showing this nuclear equation. So part 2 is split into A and B again. However, we're just going to work on them both at the same time. So it tells us that a sample of radium 224 decays to form Pb208, which is an isotope of lead. So they ask us in part A how many alpha particles are released, and B how many beta particles are released. So here's how we go about doing a question like this. So we start off by writing out the radium like we did in the last question. So 224, which is the mass number, radium, which is the element, and 88, which is the atomic number. And then this arrow is showing that it is undergoing nuclear decay. And so it tells us that it decays to form Pb208, which is lead, an isotope. So Pb, the mass number is 208. And then if you look at your tables book to the periodic table of elements, you'll see that the atomic number of lead is 82. So now we know here that we are going to have alpha particles and beta particles. So like I mentioned earlier, with the alpha particles, you can write them as helium or as the alpha symbol. You can do the same for beta particles. You can write it as beta here, or you can say it as an electron because they have the same properties. So one thing to note as well, whether you're saying a beta particle symbol or an electron signal, they both have a mass number of 0. And in terms for this equation, we're going to say that they have an atomic number of -1. They don't actually, but it's because they have the properties of an electron, so they have a charge of -1. So they're not going to add on anything to the atomic number. They're going to take away 1. So I'm just going to add here 1 alpha particle for the moment and 1 beta particle for the moment. And that's just because I'm going to add in a coefficient to those numbers to multiply them by how many of each particles we have. So to start off with, anytime you do a question like this, you start off with working out the mass numbers. Because the beta particles have a mass number of 0, they have no effect on it. So starting with the mass numbers, we have 224 is equal to 208 plus x number of 4. So 4 is the mass number of an alpha particle, so we're seeing how many alpha particles is there. So 224 minus 208 is equal to 4x. So that gives us 16 is equal to 4x, and 4 is equal to x. So that means there's going to be 4 sets of alpha particles. So now we go on to the atomic numbers. So if we rewrite it now, so we're looking for how many beta particles there is. So this was for the mass number. So the atomic numbers, we know that 88 is equal to 82 plus 4 times 2 plus x multiplied by minus 1, because we are saying that the atomic number of a beta particle in this equation is minus 1. So 88 is equal to 82 plus 4 times 2 is 8, so that's 90 minus x. So we're going to bring the 90 over to this side is equal to minus x. So we get minus 2 is equal to minus x. So 2 is equal to x. So now we know that there is going to be 2 sets of beta particles. So that's our answers then. Our answer for part A is that there are 4 alpha particles. And for part B, there are 2 beta particles. So in terms of marks, you just get 4 marks. It's 6 marks in total. So you get 4 marks for having one correct answer and 2 marks for the other one. It's not specific to which one is which. So they tell us that radium-224 has a half-life of 3.6 days. Explain what is meant by the term half-life. So the half-life of an element is the time taken for half of the nuclei in the sample to decay. So in terms of marks, this was worth 6 marks in total. So 3 marks for saying it's the time taken and 3 marks for saying the rest of the underlying statement for half of the nuclei in the sample to decay. So also just to note, as we will be using it in the later questions, the notation for half-life is T and then a little half in the subscript. So before we begin part 4, I just want to bring your attention to page 63 on the tables book. So this is the formulae on radioactivity. So the 2 formulae we're going to be looking at is the law of radioactive decay and the half-life formula. So this is them here. We're going to be using them in the following question. So in part 4, it asks us to calculate the total number of alpha particles emitted per second by a sample of radium-224 containing 4.7 by 10 to the power 14 atoms. Okay, so we start off by writing what information we know. So we know that N, the number of atoms, is 4.7 by 10 to the power of 14. And we know that the half-life is 3.6 days, because it told us that previously in the question. However, obviously, days is not our SI unit, it is seconds. So to change from days to seconds, we change it to hours first. So 3.6 multiplied by 24 hours is equal to 86.4 hours. And to change from hours to seconds, you multiply it by 3600. So that is equal to 311,040 seconds. So now we are going to first start off by using the half-life formula. So the half-life is equal to ln2 all divided by the decay constant. So obviously we don't know the decay constant yet, that is what we are figuring out. So we know that the half-life is 311040. So I've just popped that into my calculator there, and I get a decay constant of 2.228 by 10 to the minus 6 per second. So now that we have the decay constant, we can use the other formula. A is equal to lambda n. So we're trying to find A in this case. So this is your answer here when you just multiply them by each other. So this was 9 marks in total. So you get 3 marks for using the half-life formula here, 3 marks for using the law of radioactive decay formula, and then 3 marks for having the correct answer of 1.05 by 10 to the power of 9 becquerel. That is the total number of alpha particles emitted per second. So we're on to part C of the question now. So this is on modern physics once again, however it is more to do with the electron chapter. So we're looking at thermionic emission and the photoelectric effect. So this is worth 28 marks in total once again. So the first part, they ask us what is meant by thermionic emission. So thermionic emission is the giving off or emission of electrons from the surface of a hot metal. So this was worth 6 marks in total. So you get 3 marks for saying that it's the giving off or emission of the electrons, and 3 marks for saying it's from the surface of a hot metal. So in part 2, they ask us to draw a label diagram of a cathode ray tube. So this is mine here. It doesn't have to be anything perfect, but the main thing, as I always think with diagrams, is it doesn't matter how bad it looks once you have labelled everything. So it doesn't matter if this clearly doesn't look like if you drew an anode, that doesn't look like an anode at all. Once you have an arrow saying that it's an anode, then the examiner will know what you mean. So the important thing, obviously, is that you label everything. And then for this question, that you have the key components that you get marks for. So the first one is the heating filament, or if you said the heating coil. So that's here, you get 2 marks for that. And that has a low voltage across it rather. And then you get another 2 marks for saying that there is a high voltage between the cathode and the anode. You get another 2 marks for saying that the glass tube, the inside of it, there is a good vacuum. And then finally, you get the other 2 marks for saying any other detail. So it might be the fluorescent screen, or it could be the X plates or the Y plates. So yeah, in terms of marks, it is 8 marks in total. So it's 4 sets of 2 marks for each correct detail that I just mentioned. So before we begin, I'd just like to bring your attention to a few different pages on the tables book that will be important in the next few questions. First one is page 46. So these show all the fundamental physics constants. So in this case, the one we are looking at first of all is the electron mass, and then also the charge of an electron. So these values here, we are going to be using them later in the question. And onto page 55. So this is the formulae for energy and work. So we're going to be using the kinetic energy formula. So EK is equal to 1/2 mv squared. And then finally to page 61, the electricity formulae, and we're going to be using the potential difference formula. So it tells us that a high-speed electron that strikes the screen of an oscilloscope produces the green light that is seen. Part 3. Calculate the minimum voltage required across the tube to give an electron a velocity of 2.7 by 10 to the power of 7 meters per second. Okay, so we start off by knowing what the velocity is. So the velocity, which is a little v, that is 2.7 by 10 to the power of 7 meters per second. And we are looking for big V, which is the minimum voltage. So we've spoken already in this question about kinetic energy. So EK is equal to 1/2 mv squared. However, the formula we'll also be using is the formula for potential difference. V is equal to W over Q. So W is the work done and Q is the charge. However, some of you may remember, or if not, that's no worries, that the work done is equal to the kinetic energy. So they are one and the same. So that means that we can rearrange this formula here to say that W is equal to QV, and now we can put the kinetic energy and the work equal to each other. So now we need to look and see, do we have values for M and Q? So M is going to be the mass of an electron, and Q is going to be the charge of an electron. So we have our 2 values now for mass and charge. So we have everything except for the big V, the minimum voltage. So I'm going to fill them all into the equation, and we're going to work it out to find V. So as you can see here, we get our final value for the minimum voltage required across the tube to give an electron velocity of 2.7 by 10 to the power 7 meters per second is 2072 volts. So in terms of marks for this question, it was 9 marks in total. So 3 marks for having either the kinetic energy formula or the potential difference formula. Then another 3 marks for putting them equal to each other. And then 3 marks finally for the correct answer. So part 4, they ask us, how does the photoelectric effect differ from thermionic emission? So to start off with that, I just have the definition of photoelectric effect. So it is the emission of electrons from a metal due to light of a suitable frequency falling on it. So the difference between the two of them is that the energy needed to release the electron in the photoelectric effect is provided by the light. And so the difference is that whereas in thermionic emission, the heat of the metal supplies energy to the electron to do this. So this was worth just 5 marks, and you get it for saying this middle bullet point here, that the energy needed to release the electron in the photoelectric effect is provided by the light. So we're on to part D now of the question, the final part. So this is on the wave nature of light and to do with the diffraction grating. It's not too bad of a question, so it is worth 28 marks once again. So let's get into it. So on to part 1 now, they ask us to draw a labeled diagram of a spectrometer. In case you weren't sure, a spectrometer is an instrument that can be used to measure the wavelength of light. So this is my diagram here, and you can see it's not anything special, but I've labelled everything so that the examiner can know what all the pieces of apparatus are. So in terms of what things I have here that you get marks for, the collimator, you get 2 marks for that. You get 2 marks for having the telescope here, 2 marks for having the table that the diffraction grating sits on, and then 2 marks for one other detail. That might be the monochromatic light source or the diffraction grating. So that's 8 marks in total, so 2 sets of 4 for each of those details. So they tell us that green light of wavelength 530 nanometers is passed through a diffraction grating with 400 lines per millimeter. So in part 2, they ask us to calculate the angle of separation between the second order images. Okay, so starting off, what information do we know? Well, we know that the wavelength is equal to 530 nanometers. So that is the same as saying 530 by 10 to the power of minus 9 meters. So we know that the diffraction grating is equal to 1 over the number of lines per meter. However, we have the number of lines per millimeter, so we have 400 lines per millimeter. So in meters, that will be 400,000 lines per meter. So then we can find our diffraction grating, 1 over 400,000, and that is the same as 2.5 by 10 to the minus 6 meters. So the formula that we're going to be using is on page 59 of the tables book from the light and sound section. It is n lambda is equal to d sine theta. So we have most of that information already, and we know that n is the order, so n is going to be equal to 2 because we are looking for the second order images. So now I'm just going to pop in all the information we have, and we're going to work out to find what theta is. So when you get to this point here, so we found out that sine theta is equal to 53 divided by 125. So to find what the value of theta, the angle is, we need to use sine inverse. So I'll show you that on the calculator now. So this is what we get for our theta, the angle. So that is 25.08738308. So I'm just going to round that to 25.1. And make sure to have your units of degrees in there. So however, this is not the final answer because this is the angle between n is equal to 0 and n is equal to 2. And however, we want the angle between n is equal to 2 on one side of the images and n is equal to 2 on the other side of the images. So what we do for that is we simply just multiply our answer for theta by 2. So there you have it. Our angle of separation between the second order images is 50.2 degrees. So in terms of marks, this was worth 12 marks in total. So you get 3 marks for having the diffraction grating formula here, 3 marks for this one right here. You get another 3 marks for having the correct theta, and then 3 marks for the right answer at the end. So in part 3, they ask us to identify a different colour of light that could be used to produce a greater angle of separation. So you could have said either red, orange or yellow for this. Basically because those 3 colours all have a greater or bigger wavelength than green, so that would increase the angle of separation. So you get just 4 marks for saying whichever one of those answers there, red, orange or yellow. And so we're on to the final part of the question now, part 4. So it asks us to explain how the number of lines per millimetre on a diffraction grating affects the angle of separation. An increased number of lines per millimetre means that there is an increased angle. So this is to do with the diffraction grating formula. So n lambda is equal to d sine theta. However, we know that d is equal to 1 over number of lines per millimetre. So if the number of lines per millimetre goes up, sine theta itself will go up because d will decrease because d is inversely proportional to the number of lines per millimetre. So if you increase the number of lines per millimetre, the d will decrease, and because here n lambda is equal to d multiplied by sine theta, to keep that constant, if d decreases, sine theta has to increase, which in turn will increase the angle of separation. So you get 4 marks for just saying this statement here. So that's it now for this question, and it's come to the end of the video now. I hope you found this helpful, and thanks very much for watching.